So in May of last year, the San Antonio Fire Department responded to a single alarm fire, which was eventually upgraded to a 2-alarm fire, at a strip mall, single-story strip mall. We've all seen them. There was a fire in a fitness center, gym facility. The initial crews arrived. I think it was about 13 companies initially arrived at the scene. Engine 35 and Ladder 35 were two of the first ones there. Engine 35 went in on attack. Ladder 35 was doing the primary search and rescue. Engine 35 gets in there with the hose, can't move. And they're in a fitness center. You can imagine all the equipment in there. The hose is very restricted. Their thermal imaging camera went out, right? It wasn't working. It was just a whiteout. It's not an uncommon situation. So Ladder 35 is doing this primary search and rescue, advances beyond the fire hose, the initial attack. That's sort of called freelancing in the firefighting world. Typically, you like to stay behind that hose, so if nothing else, you have a tether to get back out of the building. But they advanced beyond the hose, and pretty soon afterwards, they got a mayday, the first mayday call. So everybody's ordered out for a PAR, the Personnel Accountability order. They're all out. And immediately 3 crews are asked to do the rescue intervention team, because at that point they realized they knew they were missing firefighters, but they didn't know how many, they didn't know who they were, and they didn't know where they were. Okay? So the RITs go in trying to find their downed firefighters, and then eventually they learn minutes later. What's amazing is how quickly this all happens, right? At 21:28:16, Mayday. Right after that, the PAR. A minute later, teams are going in to do the RIT. Another 5 minutes later, they learned that actually they know they have 2 firefighters missing. Okay, and then soon after that, they brought out one of the firefighters. It was the one who called Mayday, but they still didn't know who the other firefighter was and where he was. So 3 more crews are sent in to do a rescue. Again, the cameras go out. At this point, they didn't have dedicated RIT teams, so they're getting really low on air. Everyone's ordered to exit the structure. They do another accountability. They learn they're still missing 1 firefighter. In fact, one of the folks who went in to do the rescue had to be rescued himself. All right, you send a lot of firefighters in, the risk just sort of grows exponentially. So long story short, eventually the interior of the building was just no longer viable. It was burning too hot, too fast. It was too dangerous. 2 hours later, after the initial mayday, they find the downed firefighter, and of course, he was pronounced dead at the scene. And then really, unfortunately, the cause of this fire was arson. So every year, firefighters they die or they are seriously injured because they are lost or disoriented inside of buildings. Or maybe they've been injured and they cannot be found. Every day, law enforcement goes into buildings and their precise whereabouts are unknown. This ability to locate and track firefighters, especially indoors, it's a real holy grail for public safety. So in our group, Public Safety Communications Research, we're in the middle of a really aggressive $300 million R&D program that's closely associated with the development of the FirstNet network, which Jeff Bratcher was here yesterday. Maybe he mentioned some of the work we're doing in our connections. But in the same legislation that authorized the creation of that network, they also appropriated money for NIST to advance some key technologies that could take advantage of this new broadband network. 2 of them were really just sort of handed to us in the legislation. That was making sure that mission critical voice migrated from their land mobile radio networks over to this new broadband network, and also that there was the ability to interface between this new broadband network and the existing land mobile radio networks. But then through a really rigorous stakeholder engagement process, we identified some other areas where we felt our money could make the biggest impact. Those other areas were public safety analytics, and we're really focusing there on multimedia fusion and real-time information. Also, user interfaces, so new ways to interact with all this data they're about to get, and the new types of devices they're going to get, and really focusing on that user experience. And then the other area that was identified was location-based services. And within that area, we're focusing on a few key technologies. What this map here shows you is just kind of some of the breadth of the engagement we're doing. To this point, we've put out a lot of research grants and done a lot of prize challenges. You can see this is a worldwide effort. All of these dots represent, companies or universities, institutions, or public safety organizations that are being funded by us to do research in these areas. And if Paul goes up to the filter, the top left there of this map, there we go. We can select location-based services, and we can see kind of just the breadth of the work that's going on just within that portfolio. And again, you see it's worldwide. We've got things going on in Melbourne, Florida, Melbourne, Australia, China, England, all over the place. So it's a really exciting effort, a lot of energy, a lot of new, part of the thing we're doing with these funds is really trying to build a new public safety R&D ecosystem. So a lot of these folks are just new to public safety in general. So it's bringing a lot of new energy and ideas and innovation to the mix. I think we'll go on to the next slide. So what I'd like to do is talk about the areas that we're investigating in location-based services, and specifically related to indoor mapping, indoor tracking, and indoor navigation, and kind of relate them back to that incident in San Antonio. So one of the things that was, as they go through you read through the fatality reports done by the National Institute of Occupational Safety and Health, or NIOSH. They have a great firefighter fatality program that goes and does post-incident reporting. They discovered they didn't have a pre-plan for this particular facility. Why didn't they have a pre-plan? Well, it's very difficult to do for the first thing. It's very time-consuming, very complicated. There's tons of square miles that each of these jurisdictions is responsible for. Okay? Well, what if there was a better way to do these pre-plans? I mean, if they had a pre-plan, they might have discovered some things right off the bat, which is the way, the front and rear door, and there was an interior door that they didn't know about, and they would have seen a lot of the clutter inside the fitness center. Then who do you send in and where? Very risky proposition. So something that we're focusing on is the use of LiDAR and 360-degree imagery to go into spaces and capture 3D images and models of places, of structures in real time. So what Jared here is modeling for us, and I mentioned to Jared, this could be a start of a very fruitful mobile modeling career. He's a good-looking guy. I mean, this could be something for him. This is a mobile mapping system. And what you see here is a LiDAR, or a light detection and ranging system, spinning around. It's got 32 laser beams, this one. So yes, we are shooting you with laser beams right now. And then there's a 360-degree camera on top. So here's the deal. To do indoor location tracking, you need indoor maps, right? So indoor maps are very difficult to get. A lot of times when they do these pre-plans, they're handwritten reports. They might draw a little sketch. Very rarely do they actually have a floor plan of a facility, much less all the other information that you need about a structure. So they're difficult to get. First responders are already walking through a lot of these facilities as part of their pre-incident or pre-planning operations, so why not give them a way to capture this information in real time and then do a whole lot more? So what Jared, we can see right here, I'll just kind of try to show you, if you kind of walk around maybe a little bit, I'll move this. Someone in the front row can see it, but what's happening right now is he's collecting information about this space, and you can see about 75 to 100 meters reliably. And as you walk through a structure like the Memorial Center, you can map the whole building and have a 3D model when you walk out. But the coolest thing about this is that that's just the start of what you can get. Here's an example in the top left corner of the floor of one of our buildings where I work. You can see it's pretty darn detailed. There's a lab there, a bunch of cubicles. That's just one floor. If you look on the top right here, you can see a 3D image of this whole building, and there's a yellow trace there. It's probably too hard to see. You can probably bring the lights down maybe to help see that. There's a yellow trace there. It shows you exactly where you walked. On the bottom left here, you can see a 2D cut of a floor plan. It's not as precise as you'd get from like a CAD model or something like that, but it's pretty darn good, right? And then something that's really cool on the bottom right here is change detection. Okay, so let's say you had a floor plan, you got it once. What are the odds you're going to get another floor plan when the building owner does a remodel, right? Pretty slim. So what this allows you to do is every time you go back into a space, you're updating, you're getting real-time information about that space. And so this change detection feature, you can load up your reference map. When you revisit the facility, you will immediately see what is different. What's that wall? What's that new piece of equipment that you've got that could be a real big hazard that the fire department needs to know about? So those are just some of the really interesting things you can do sort of after you get this data. Thank you, Jared, for coming up here. Give a big hand to Jared. But there's a lot of other really cool things you can do as well, right? You've got this model. What if you load that up into your VR system and you train? You do immersive training in the very same environment you might find yourself in. You could attach an LTE phone onto this and capture the signal strength of your FirstNet, let's say, walking through these buildings. You could do, you've got a 3D model, which you could hand to people who could look at the flow path, flow dynamics through a building, very important to firefighters. So there's all kinds of value-added things that you can do with this data, and that's one of the big points. So we kind of call this the future of pre-planning. So a couple other, and one very important thing I didn't mention, automated object detection. You're going through this building, you've got a camera. The object classification is going crazy with, Facebook and Amazon and Google. They're all doing it, right? So you don't have to sit there, you shouldn't have to sit there and annotate that here's a standing water pipe or here's this utility panel. You've got a camera on there. You can classify it, you can recognize it, you can label it, and it should be on the map, geotagged, ready to go. And you could label scenes as well. You get a collection of these objects that you pull together. Now you've got some scene semantics. You can say this is a lab, this is an office, this is a there's oxygen tanks, this is a very hazardous space, things like that. So a lot we can do with this data, a very exciting space. All of this depends on the continuing decrease in cost of LiDAR. The automobile industry is dumping billions into this space because LiDAR is a key part of the autonomous vehicle future. So that's happening, and what they're really moving towards are solid state sensors, which is, again, going to really decrease the cost. So a system like what Jared had on, a little pricey right now for a lot of departments, but we are seeing the cost of these 3D mobile mapping systems really decrease, and the amount of things that the technologies people are adding to this space, it's incredible. Every day, if you read the trade journals, it's just something new ways to make things like object classification easier and easier. Very exciting. Of course, what we want to see for public safety, what we're driving towards is you come and get that data, you press the red button, the magic button, and everything just happens. Right? We're not there yet. There's a ways to go, but we are working towards that future. Okay, Paul, if we can go to the next slide. So the other thing we're really spending a lot of time on is indoor tracking, right? Going back to that incident. Despite, if you read through these reports, there's so many things going on. These are such complex operations. What's going on with the RIT team, the pre-plans, all these SOPs, incredibly complex situations, and these reports always have a ton of recommendations. But the bottom line is this. Even if they didn't do all of that stuff, like maybe they thought they should, they were supposed to, or they're being recommended to do, if they had the ability to track the first responders indoors, nobody would have died, most likely, okay? And ironically, these reports typically don't mention as a recommendation, let's develop an indoor tracking capability, because they really focus on what can be done right now. But we're spending a lot of time and energy and investing a lot of money in this space. So what we've got, for example, are universities who are developing ultimate navigation chips. The top left here, it's taking a bunch of different sensors and putting them in a three-dimensional chip. It allows you to develop much lower cost single-dimensional sensors like gyroscopes and accelerometers. You package them in a 3D way, and you can combine this with a bunch of other different signal types and sensors, and you develop this, again, a low-cost navigational grade chip that could be inserted in a lot of different devices. In the middle here, you see this boot with a prototype. This is just a test sort of unit. What this is, it's an inertial measurement unit. Again, it's got accelerometers and gyroscopes in it. And the thing about, if these inertial, by the way, these are all in your phones, right, in your back pocket. So when you're walking through a building or outside, you can see your movement, right, in real time. Well, the problem with these sensors, especially in these low-cost commercial ones, is they drift. It's called drift. They get off track very quickly. I mean, tens of meters in a matter of a minute. Okay? Now, if that technology worked, we'd be done. This would be a game over, problem solved. There are much higher quality inertial sensors, but you start to get up into thousands of dollars, tens of thousands of dollars, hundreds of thousands of dollars, until we're on talking about things that are on rockets, potentially millions of dollars. So what we really want to try to do is get these inertial sensors down to a more of a commodity price point that are then what we could call navigation grade. And interestingly enough, one of the techniques that shows a lot of promise is that if you take these inertial sensors and you put them somewhere like a foot, where it experiences a zero velocity moment. It's called a zero velocity update. As I'm walking, there's a point where my foot it's not moving, it's zero velocity. And if you can sense that, you can sort of recalibrate those inertial sensors and say, I'm at zero velocity, so that constrains this drift. So what this team is doing is looking at that technique in a lot more detail and looking at different parts of the boot. Where does it work? And then again, firefighters are on their hands and knees most of the time inside a building. So how does it work when they're in those sort of mobility modes? How does it work when you're sliding downstairs? Things like that. So very exciting. They're looking at LTE, for example. We talk about FirstNet. The accuracy from a cellular network that you can get is not enough for the requirements of first responders. However, it can be added to this sort of multi-sensor fusion solution to give you some constraints. Again, and if it's everywhere, that's a big aid. What here you see here is just a track, the true track in green, and then what they got with a combination of an inertial measurement unit and using LTE. You see it's pretty darn good. So a lot of promise there. We've got a group that's looking at something really neat using visual odometry is what it's called. So it's using a camera or visual sensor to actually track your movements. Okay, now if for a law enforcement, that could work really well just as is, especially with all the body cameras that are out there. In a fire, not so great, right? But what this group is doing is looking at thermal imaging cameras and using those to actually do this visual odometry. And so they're finding, and they're using a lot of machine learning approaches to sort of aid this. That's one thing you'll find in this, just like any technology, machine learning has permeated everything. So our groups are using that as well. So they've got a prototype here where they've mounted a 3D camera, and they've got this on top of a thermal imaging camera, and they're using a combination of this machine learning and the TIC to basically study what they can do inside a smoky environment. And what's really neat about this as well is they're also training their algorithms based on sort of more of a constrained motion algorithm, like right-hand searches, left-hand searches. They're the first people to do this. So when you constrain the solution a little more, you start to get more accuracy. So very unique. And then we have some other groups. A lot of groups are looking at ultra-wideband technologies. The reason I pulled this in here is ultra-wideband is very wide bandwidth. Because due to some signal strength issues with the current licensing, FCC licensing, doesn't go that far. However, it shows it's very accurate, and it shows a ton of promise from a cooperative ranging standpoint. So let's say that they always go in teams, and there's a bunch of them in there. If you could, maybe I don't have a really good location at the moment, but my teammate does, or another unit over does, and I'm close enough in this building to actually get a good ultra-wideband signal from them, we can cooperatively localize each other. So again, it's another constraint that helps narrow down where an individual is. So this idea of doing cooperative localization, it's not being done anywhere else, as far as we know, except in these applications. So what I want you to kind of take home from here is that there's a lot of work in indoor location tracking in different industries: healthcare, manufacturing, logistics, entertainment, you name retail. They want to know what aisle you're in, right? So they can flash you that sale. But this use case is way harder than all of those. And so we are, for the first time, really, as far as we know, spending a lot of time, energy, and money on really trying to solve this problem. And we've got a lot of very talented people working on it, a lot more work to come of this. Traditionally, the way that these things have worked is you deploy Wi-Fi or Bluetooth beacons in an environment, and you do what's called fingerprinting. It's very time intensive. You walk around and you measure the signal strengths of all these locations, and then you kind of know where you are based on your proximity to a Bluetooth beacon or what you're getting from all these different wireless access points. But that was not going to work for first responders, right? We need an infrastructure-free solution. You show up to the site, there's no power, there's no external requirements, you show up and the thing just works, okay? So again, another real difficult part of this problem that we're trying to solve. I guess we can go to the next slide. Okay, so now let's say we've done all this work, we've invested all this time. How do we know these things work? Well, NIST is very well known for its measurement science. capabilities. So something that we're focusing a lot on is measuring these indoor localization systems. So on our campus in Gaithersburg, we actually have 5 buildings that have precisely surveyed dots all over the floor. We call these control points. So we can take systems through there and we have a ground truth. And so as we go through with the localization system, we can measure where you are. We're also adding, so these facilities represent like warehouses, underground facility, a high-rise, a typical sort of 3-story office complex, a real range, because that's what you need, right? We're also adding, we have a really neat facility on campus called the Net Zero facility where they study energy savings in a typical home. We're adding that to our mix as well because residential is so important for this problem, especially for firefighters. So one of the reasons you need this real diversity is that within structural fires, by far the highest number of fatalities occurs in residential properties, and that's because there are by far and away many more residential fires. However, the risks are far greater in commercial structures. If you look here, deaths per 100,000 fires, manufacturing, public assembly, stores, et cetera, much, much higher. So we need to be able to measure these systems in a range of facilities, and we are doing that. Okay, I think we can go to the next. So we talked about indoor mapping, indoor tracking, now indoor navigation. What if they had been able to, so you've got a down firefighter, now you got to go find him or her, right? How do you do it? What's the best way to get through the building? What's the most efficient way? That's still a problem in itself, right? So indoor navigation. So Denver has a great public transportation system. Hopefully many of you were able to take it from the airport to Boulder, right? If you anybody fly on Southwest, and you land in a Concourse C, right? Go to your phone. I want to get to the bus station. So you put that in, and here's what you'd be really surprised to find that from Concourse C to the Denver airport station, it's actually an 11-mile walk across restricted use or private roads, and it's got a 1-mile drop, and then you got to climb up another mile again, right? So to say that indoor navigation has a ways to go is kind of an understatement, right? I'll go to the next slide. So we are doing a lot of interesting things in this space as well. Specifically, probably the most interesting project we have is working with the Open Geospatial Consortium, who is represented here as well today. And so